Swayam Prabha. Digital India. Educated India.
Thank you, Professor Monica. It was very nice talk and a lot of things to know, to understand. And as Professor Monica tells you that it's not like a nationwide problem, it's a global problem. Like for example, it's not that CO2 is more in other countries and in India more, in other countries less. So it's the same. So we have to, as a global, worldwide, we have to fight with this. So I'll mainly talk about CO2 emission from industry, because industry CO2 emissions, I think Professor Monica tells about different emissions, how much emission and carbon footprint. And one of the footprint or CO2 emission is coming from the industry. So I will mainly talk about how to tackle CO2 emission from industry. So this is more about like a technical talk, like fundamental talk. So I'll talk different techniques or different processes, different technologies to tackle this CO2 emission from the industry and why it is important. I'm audible to everyone, right? Okay. So yes. So first, I think already you got a brief introduction about the CO2 emissions. I'll just give you just briefly the global emission, as I think it's increasing day by day or year by year. There is a lot of evidence of changing climate change, which can be also listed in NASA climate change. If you see in this, for example, here, okay, this climate NASA evidence, there are a lot of evidence. For example, global temperature is rising. If there is a report that in 2016 and 2020 is the warmest year, because due to it was reported that this is the warmest year because of the climate change. For example, sea level rise, all these are the recorded in this database, or these are the facts. And extreme, for example, extreme events, which all of us, I think, were like experiencing. A lot of cyclones, even in Chennai. If you live in Chennai, there are a lot of cyclone. Number of cyclone has increases. Number of rains are increases. So you can see, or the temperature, for example, it's very high. So you can see the extreme events we experience day-to-day life, this climate change problem. So what should we, how to tackle it? So these are the key milestone. I think you already know about all this key milestone, milestone of IPCC. I'll just maybe talk about the main one, which is, I think in India it is important, like for India's turning point, which is COP 2026, COP 26, where the one of the pledge India has pledged to reduce the CO2 emission or net zero emission by 2070. So there are a lot of activities are going on this CCUS because of this. So I think from last few years, there are a lot of initiative has taken by the government to work on these areas also in India. So these are just key milestones. I think you already aware of these milestones. So I'll just skip. So now the source of emissions. I think Professor Monica has talked about the CO2 emission of different sources, but I would like to highlight the main CO2 emission coming from, for example, energy industry, which is our light, for example, electricity. Those things are coming from energy industry, coal power plants, especially in India. If you say, I'll mainly focus on India so that we can relate. Then chemical industry, which is also an important. Steel industry, all the buildings, road, bridges, we cannot live without that. Like Indian development, nation development is based on the development, steel and cement industry, like big buildings if you see. And transport, day by day, I think transport is increases. So you can see even in Chennai, there are so much traffic. So every people has almost a vehicle. So changes are happening. I think there are a lot of initiative is taken on EV nowadays because of this. But these are the industries. If you see energy industry, chemical industry, steel industry, cement industry, these are hard to abate industry. For example, even if you tackle energy somehow, like for example, go to the renewable, how can you deal with cement and steel industry? So these are very hard to abate industry. So best option is that, we can do something for example, next slide, that's come the CCUS, carbon capture, utilization, storage. We cannot, for example, these are hard to abate industry, we cannot stop this production, but we can do something so that we can retrofit something so that we can say capture the CO2, utilize the CO2, some value added product, or store it. So these are without drastically changing this, the potential, drastically changing their dependence of this industry. So that is the scope of this work, like carbon capture, utilization, storage. So I'll mainly focus on carbon CO2 capture. I think Professor Monica is dealing with the storage part, and I also utilization part. So I'll mainly capture what are the different technologies available in the carbon capture, and I'll give a brief glimpse of IIT Madras, where what are the activities are going on in the IIT Madras. I'll just give you a brief glimpse about that. I think this picture, so this is just to show, like for example, CO2 is come from point source or direct air capture. Point source means from the industry. This is transported, either we can capture at the source, like which is coming from the flue gas, you can capture it here, or we can capture as a direct air capture, and then transported, and it goes to the sequestration in the ocean in terms of hydride, or also it can go to the enhanced oil recovery, or it can go store in the saline aquifers, or it can be used for utilization, some value added products. For the fertilizer industry, there are a lot of use, also mineralization, CO2 mineralization is also CO2 utilization. A lot of work and some value added product, it's okay, like a methanol, formic acid, all these things. So this is just a roadmap of CO2 utilization. But if you see the cost distribution, this is again, it's get from this literature, the capture cost is maximum. Like for example, in CCUS, if you see, the capture cost is again, it's 63% of the total distribution cost. So we need to focus on the capture. So in this talk, I'll talk about mainly different technologies available for the capture, for CO2 capture. So different CO2 capture routes are absorption, adsorption, chemical looping, membrane, and there are also cryogenic also capture. But I think I'll mainly talk in this 1 hour mainly about adsorption, membrane, and absorption. Okay. So absorption it's commercially, it's the most mature technology. You can see till now, where I think a lot of industries has used this absorption, which is implemented in the commercial scale. But the rest, membrane, absorption, and those are still not commercially that is popular. Okay, that's not that matured for industry. So, but I'll talk about all this technology one by one. First, I'll talk about absorption. What is absorption? So, how many of you are chemical engineering background? Only one? Oh, most of us. Okay. So, yeah, absorption is. Okay, correct. Yeah, it's here again. It's written here. It's a gas. The gas phase, the molecules which for example, here the solute, which is like in this case, it's the CO2. It's absorbed into the liquid phase, liquid film. So, and there is a mass transfer happening between the gas and the liquid phase. Okay. So, the mass transfer steps for the CO2 capture process has like 4 different steps. If you see the gas, initially this is CO2 gas, then this is a liquid film. So, CO2 is diffused into the liquid film, and then again this is a mass transfer is happening, diffusion is happening. Then from the liquid film it is dissolved, the CO2 is dissolved in the liquid film, and then again back to the film to the liquid bulk, it's diffused, and if there is a binding element there or binding, then it react in the liquid bulk. So in this step, it's like a diffusion happening, dissolution is happening, and reaction is happening. So if you can see that in absorption process, 3 different, for example, mechanism is very important to understand the process. One is the mass transfer or diffusion between gas and the liquid. One is the solubility of CO2 in the liquid, solubility of CO2 in the solvent, that's why we find out pKa and everything. And then chemical kinetics, how the CO2 will react with the binding constant or whatever the, not binding constant, binding element. Okay. So these are the three different processes happening in the absorption process. This is just, I'm giving a brief fundamentals. Okay, then next, most commonly used absorbent is amine because it has carbon atom, hydrogen atom, oxygen atom and N atom. If you see here, the most commonly is amine used. So maybe you heard about, I think, when talk about solvent base, absorption base, MEA, I think whenever you talk about we can solve it like MEA user, it's called, this one is monoethanol amine, which is like a first generation amine based absorbent. But with the new development also, there are new primary, there are new blended amine or primary amine, said there are also secondary amine, tertiary amine. But first it was like MEA was used, it's a first generation amine and it is a primary amine, okay, means one bond, NH bond is 1. For example, here if you see NH bond is 1, secondary amine there is 2 bond, tertiary amine is 4. So this is again, I will not go into the detail, but if you are interested you can ask me. But the main reaction is that CO2 react with the amine molecule, this is the amine molecule, and this reaction is reversible reaction, okay. It forms, this is a jitter ion and then jitter ion is converted to a carbamate. So this is a general reaction scheme from CO2 to the primary amine. There is a two-step process, and if there is a hinder amine, this is another scheme, general reaction, where amine is react with, again, it's a bicarbonate form. So these are again reversible reaction, but when this is again when it's CO2 react with the amine, it's exothermic reaction. But when you give the reaction, endothermic reaction, when you give reaction at high temperature, again it dissolve, means again it break the bond and then you can get CO2 back. So these are reversible reaction. Why MEA is usually used? Why not other solvents? Because it has a high chemical reactivity of CO2. Okay. So this is just about MEA, which is most commonly used in the industry or most commonly used for CO2. There are also non-amine based solvent, for example, sodium carbonate, ionic liquid. There are a lot of research is going on ionic liquid. This is a new, and there is also new blends, for example, combination of primary amine, secondary amine, tertiary amine. So there is a lot of new development of solvent is also happening. I am not included in this slide, but there are always there are new, like a new blended amine, biphasic amine, ionic liquid. There are also some natural amine, bio-based amine, bio-based not amine, bio-based solvents. So there are a lot of research is going on this. So this is a solvent based or absorption based CO2 capture, you can say. So this is about just fundamental or how the reaction. So now how the process. For example, in this case, I think all the chemical engineers must have an absorption tower and stripper tower. Right? Okay, so this is an absorption tower. So what happened here? This is filled with amine solution. Usually again 30% of amine and MEA or 70% of water is used. So, and your flue gas, for example, CO2, which is coming from the industry, CO2, nitrogen, NOx, SOx, the flue gas is fed here, and your reaction is amine, CO2 is absorbed in the amine, and then you get a CO2 rich gas here, and CO2 laden, absorbed CO2 absorbent is again back to this desorption regeneration tower, where you send the steam, like a heated steam, or you give a temperature, and then the CO2 is dissolved in this regeneration tower. Again, then amine, the regenerated amine, which is the CO2 is coming, then CO2 is separated because CO2 is break from the amine. Now, in that gas, there is no nitrogen or no other impurity, only CO2. So, CO2 goes for utilization or storage. This is like a free CO2 coming, okay, pure CO2 is coming. And then this amine, whatever is regenerated back, the CO2 free amine is again pumped back to in the absorption case. So this is the absorption process. Okay, so again, this is the absorption process. This is a simple process. Absorption and desorption is happening. It's not nothing new. It has been used for many years. CO2 is absorbed. CO2, that is react with amine, this NH group, the CO2 is absorbed. This impurity, if there is an impurity, that's why it's very important to remove the impurities before sending it to here. The industry, you are using this technology. Okay. It's great. Yeah, I think, but here one more, I think a figure should be there. It's like a pre-treatment unit. We also use a pre-treatment unit here. So usually you treat pre-treated remove, because again, if it's like SOx and NOx, there again, there is high chances is like some toxic gases is forming, so which we don't want. So remove the impurity first and then flue gas. So that is the process. But absorption process for CO2 is this. Challenges, again, this is again mature technology, but there is also a challenge. So main is like, one is salt formation because of the carbamate formation, which like operation is difficult. And then another is amine degradation. For example, when you are using cyclic operation, right, one is amine absorption and goes to the desorption, again regenerate, then it's degrade. Okay, it's your absorption capacity will be decreased, and also degradation. For example, one more I think impurity I forgot to tell, that oxygen. If there is a oxygen, then it also degrade faster. Amine degrade faster. There is like a thermal degradation and oxy degradation. For example, degrade faster. Again, NOx, SOx, you are talking about the impurity. So this amine degrade, which again you reduces the absorption capacity. That is another one problem that reduces the absorption. Another problem is that this amine degradation product, the degraded amine is very corrosion affinity. It's very like, if your material of construction, it is very like, it can create this corrosion. It has an affinity towards the metal of construction. So the most challenging part is, for example, the corrosion of the amine equipment, because of the salt formation, also for the amine degradation which corrode. And again, if you have to change your reactor every few years, then again so much money lost, right? So that is again a challenge, the corrosion due to the amine degradation. And solvent, again regeneration is very costly because you are removing CO2 from the liquid. So regeneration is very costly. Another is, we talk about energy, but there is also main problem is the water. Energy requirement is high. We are always count as like energy requirement. But if you see in the modern world, water is also very costly nowadays. Water is also scarcity, right? So, but here we are using lot of water. 70% of water we are using. There is again, it's like it's not recyclable. So that's, we are not getting a fresh water. So that's water usage is very high. So this is the challenges for this amine absorption based CO2 capture. Okay, so what are the next? But this is the most mature technology. Yes. Why? Because this amine is, for example, MEA, only 30% MEA is used. It's 70-30% MEA use. Again, it's because on the thermal stability or the absorption capacity. So we mix the MEA, 30% of MEA and 70% of water. So that 70% is your water. No, it's not, because steam is again, because of here we are using steam, right? But here in the main fresh amine is also 70%, it contains 70% of water. So this solvent is the mixture of 30% of MEA and 70% of water. So here main. Steam is also coming from water. This is also energy. You are right, because steam is again coming from energy. So a lot of usage of water is high. For 70% plus also steam. Steam is also coming from water. Okay. For example, is an exothermic reaction, temperature and pressure maintenance, it's operational problem. So that is again a big challenge. Okay, thank you. It's a nice discussion. I think so for example, for corrosion, a lot of other issues using saline water. Thank you all for discussing this point. So challenge, yes.
What is the need of using water in a reactor, ma'am? What is the need of using water in reactor? Actually, amines are hydrophobic, no?
Okay, next go to, this is lot of challenges. Now we understand absorption process. Now I would like to discuss about another technology. For example, absorption. It's, if a change is that AD, it's called absorption. Now again, you know it's about absorption. This side I will like to ask. Difference between absorption and absorption. Again, absorption is a surface phenomena. If you see, it's not dissolving. It's not solubility like that. The CO2 is dissolved in the liquid. Here, it's not absorbing. It's a surface phenomena. This form. Another like a quiz, for example, this is two empty, for example, empty column, for example. We put empty column and this is with some absorbent you put, and then you inject the CO2. So, which will absorb or which will store more CO2? The first one or the second one? Huh? Second one. Okay. Yeah, correct. The first one, because it has the absorbent. That's why. Okay. That's why it's okay. Again. So this is again a gas solid. Here, these absorbents are the solid porous material, porous material which absorbs CO2. Again, absorption is, mechanism is that this is a gas phase. For example, this is a porous material, solid, and then this is a bulk solution. This is a gas phase, and it deposited on the surface of the solids, the particles or solid, solid pellets or solid particles. So if you see this monolayer, multilayer, again it based on that lot of isotherms form, monolayer isotherms, and if there is a multilayer, I'll not go into the detail, but yeah, it absorbed like that. Again, mass transfer is happening. Here the mass transfer is again the three process. One, it is mass transfer happening in this gas phase to here in the surface, and then in the macropores too means that the pores between the particles, macropores first into the gas film and the pores between the particle, and the third one is into the micropores. So CO2 is also stored or absorbed into the micropores of these particles. Okay, so there is again a three-step process. First is happening between the gas film in the surface, it's monolayer or microlayer happening, and then it absorbed in the pores or in between the particles, and then in the micropores of that particles. So again, this is the mass transfer process, absorption mechanism. Again, two different types of absorption. One is physical absorption, which is a weak intermolecular bond, for example, van der Waals bond between the CO2 molecule and the surface, the sorbent molecule. So there is a weak intermolecular bonding is happening. This is called physisorption. If there is a covalent bond between the active site and the CO2 is forming covalent bond, it's called the chemisorption. If there is a reaction between the active site and this CO2 molecules, then it's called chemisorption. So this is the fundamentals of absorption. Again, there are many common types of sorbent. Again, there are a lot of development is happening for sorbent material. Commercially available, I can say that activated carbon, zeolite, silicate, MOF. There are a lot of research is happening on this metal organic framework, and a lot of functionalized the zeolite or functionalized sorbents are developed, or research has been going on. So there are a lot of sorbents are available in the community or for this absorption, and a lot of research is going on. But exactly you can see CO2 is absorbed at the surface. So adsorption is a surface phenomena. Now again, process similar to absorption. This is again it has an absorber and a desorber. Absorption, you fill the absorber with the solid material and then you inject the raw fuel gas, and CO2 is absorbed here. It's an exothermic reaction is happening, and then you can see the CO2 lean fuel gas is coming. CO2 rich product and again go to the desorber, absorbent, and then there is a two different process. Either you can increase the temperature. because CO2 absorption is mainly related to temperature and pressure. So there are two methods. One is temperature swing method and another is pressure swing method. In the, for example, temperature swing method, you inject the CO2 here and increase the due to the exothermic reaction, temperature increase, CO2 is absorption happening. In the desorption, again, you increase the temperature and the CO2, this weak covalent bond or weak intermolecular bond, it break and CO2 is, for example, it's dissolved, or CO2 is, for example, the break is born and you can get only CO2. So you can regenerate, you can again use the particle, the solid particle, porous particle in here. So this is a temperature swing method where your temperature is changing, your desorption is happening due to the rise of the temperature. Another is pressure swing absorption, where your temperature is maintained but your pressure is changing. You are, for example, in the absorption vacuum pack, you give a pressure for that absorption column, and you then at that pressure the CO2 is absorption happening, and then in the desorption column you release the temperature and then your CO2 is released from your sorbent particle. So there are the two different particles. One is thermal swing or temperature swing, where your temperature is increasing and then decreasing, and here pressure, at the high pressure its absorption is happening, then you release the pressure and then your desorption is happening. So these are the two different processes for absorption. Okay, till now? Yeah. So chemisorption, for example, lot of solvents are available, for example, amine impregnated with zeolite or silicate, aminosilicate. Those are you have a amine component there, or you grafted there or impregnated there. So those are chemisorption. So you are like their NH group in the amine react with the CO2 there. So though they can be regenerated, but more energy is required because you have to break the bond, covalent bond. So more energy is required for that. Okay, this is the absorption process. Again, these are the process, but there are again challenges. Absorption, again degradation is also happen if you reuse many cycles. Another problem is attrition. I think when you use in the large scale, the particles are moving and again they collide each other. So there are this particle again porous material. So attrition is, it might break. Attrition is like that. The powder, it may break or attrition happen. The powdery type powder can come, and it might again the operational pressure drop can be increased, and also it might block some of the your for example openings and also the outlet those. So attrition is a big problem when you go for a scale up. That's why it is not commercially that much popular because of the particle attrition. First of all, like because this particle again when you run cyclic operation, you run one cycle and two cycles, this particle break and lot of the particles or lot of powdery type forms, and then which increases the pressure drop increases more energy, and also it might clog maintenance, you need the reactors to be maintained. So those are the problem in this technology. And compared to amine, you can say that it has a lower absorption capacity compared to amine. And it's again, this is a gas solid problem, pressure drop and temperature maintenance is also very difficult here. It's an exothermic reaction, packed bed reactor, pressure drop is very high. And also the temperature, exothermic reaction temperature is also rise. So maintaining the pressure and temperature in this reactor, and sometime what happen at high temperature there is hotspot generation is also happening. And then the particle, like for example some particles are agglomerated and make a, for example, no gas can flow through it. So hotspot generation is another technology I'm talking about is membrane based technology. Membrane based technology is again, it's a membrane is kind of filter, it's allow the CO2, for example, this is just if you consider a membrane in a simple form, it's like a filter, it's CO2 is coming, fluorism blue is nitrogen, for example methane, it's only allow the CO2 to pass through. It's like a membrane, you can say it's a separation also, not capturing. So you only, these membranes will allow only CO2 molecules to pass through, not the nitrogen and methane, which is related to the mean free path of the gas molecules. Okay. So there are again different mechanism for CO2, for example, for membrane also pass through. First, I'll talk about the convective diffusion. This is a membrane. This is like a pores in the membrane, if you can say. Here no separation is happening. You can see the CO2, the blue one is a CO2 if you consider, and the black one is the nitrogen. So everything is passing. So no separation is happening in this convecting. Another is constant diffusion, which is again between 10 and 100. This is a pore size, nanometer, which is if the pore size is less than your mean free path of the gas molecules, again which will allow only the black one if you see, but they don't allow the blue one. So again it's based on the selectivity of the molecules. Third one is kind of molecular sieving, which is you can see it's the pore size ranges is 0.5 to 10 nanometers. So again it's different separation or diffusion processes. And another one is the solution diffusion. For example, in the membrane, they permeate, they pass through the membrane and then it diffuses through the membrane and it goes through the, for example, the blue one, if you consider it is passing, it's dissolved in the membrane and then it goes into the here. And here, felicitated transport. There is like, for example, in membrane, these are different type of membrane I'm talking about this, they have a mobile carrier. So it is, for example, some compound or something, it carries the blue molecules through the membrane. So these are the different mechanism for membrane technology. I'll not go into the detail again, but it has lot of challenges. First challenge is that membrane, it's very costly technology. Membrane, if you have to select only for particular molecules, so you have to again design a specific membrane. And for example, it's good for when there is a high concentration of CO2. For low concentration of CO2, for example, 20% is considered as like a low concentration of, it's high energy consumption. You have to do more sieving or you can do mole filtration. Sometimes you have to do 2-stage, 3-stage filtration, then only you will get the pure CO2. It is sensitive to the moisture. High temperature of the fuel gas might degrade this membrane. And scale up is a problem. Again, it's a filter. The scale up issue, if you see so much gigatons of CO2, if you have to capture, how many membranes filters you have to build. So the scale up is again one issue. And it depends, it's very costly as that the permeability and selectivity of the polymeric membrane is very crucial for this case. So it's a costly technology. So I think these are the three technology I'll talk here. I think there are also cryogenic CO2 capture technology, bio-based technology, chemical looping. I think it will be I'll be discussed in the next CO2 capture class. So here I'll just concentrating on these two different technology. Before that, yes,
one question.
finishing, I would like to just give you a status of CCUS. This is again, it's a little bit old data, I think 2020 data. There are a lot of CO2 in the world operating and under construction. Significant is improving near worldwide. But I just wanted to highlight there are a lot of, for example, blue one is under operation and dark blue is in under construction and green is in early development. So there isn't for example, there are a lot of work is going on in 2010 and 2022 in last couple of years. But again, we need all to be operate to capture so much of CO2, right? This is just the database. I like to show you the India, I think CCUS in India. So I think here, I got this map from global status of CCS. So here if you see, there is only one spot we can see here, which is in, I think again in Tamil Nadu it's Tuticorin Alkali Chemical Fertilizers, which is the first industrial scale pilot plant, capture and utilization. In India, it is 164 tons per day. So it's in the global map, there is only one point. If you see only one Indian capture and utilization unit. But if you see more into detail, there are also some other, for example, Tata Steel has recently also have a carbon capture unit, which is 5 tons per day, and some utilized in Uttar Pradesh. There are some fertilizer plants which also commercialize, or there is a plant for CO2 capture. So this is, I just wanted to give you an overview of CCUS, status of CCUS in India. Yeah, so we are not doing that great, but we are just compared to the other world, for example, US or here Europe, we are not doing that great, but just we are starting. We are just in the initial stage, you can say that. The CCUS in IITM. So there is a CCUS demonstration unit, both adsorption and absorption. The technology what I talk about, absorption, it's there. So it's, I think, near Sudha Shankar building. If you send, there is a 2 different unit. I think if you have time or slum slot available, you can go for a demo. There you can see both absorption and adsorption both unit. So we can arrange that. If you are interested, we can do that. Okay, so this is a MO unit. This is again part of Energy Consortium. The next, I would like to talk about also my research. Since I am talking, so I would like to also show some activities of CO2 capture which is happening in my group. For example, this is an absorption, CO2 based absorption. Again, different sorbent, development of different sorbent. We are talking again, said there are a lot of development is going on. One of the problem is attrition. So how to reduce the attrition, that is one problem. Again, one of the main challenge is the high pressure drop, because these are particle gas in this kind of packed bed reactor. The pressure drop is very high. Pressure drop is very high means high energy, and also the maintenance is very difficult, for operation is difficult. So we wanted to do some like different structures of sorbent so that we can reduce the CO2, the pressure drop in the packed bed reactor. So that is the work, one of the work going on. And again, this the gas solid flow can be like, for example, it can be as a packed bed. It can also fluidize. Like packed bed means it stays still, it's not move. Fluidize means if you increase the velocity of CO2 or flue gas, it will fluidize so that your pressure drop will be less, but absorption capacity will suffer or will be a little bit less. So you have to find the optimum, for example, operating condition between CO2 capture capacity, absorption capacity, temperature and pressure, all these things. So all my work is on packed bed, fluidized bed, and also multi-stage fluidized bed. For example, if you combine both packed bed has a advantage of higher absorption capacity, but fluidized bed has it has a temperature distribution and pressure distribution is good. So we wanted to combine. So this is the multi-stage fluidized bed where you have both the advantages of high absorption capacity, and also this pressure drop is less compared to your packed bed reactor. So on this front, I am working to develop new reactors. This is multi-phase, and again the complementary CFD simulations for absorption based to fluid model for the scale up studies. All these these are the research going on in my lab for absorption based CO2 capture. If you are interested, you are feel free to visit my lab also. It is multi-phase flow porous media lab. It's in CHL. So you are welcome to visit one of these the processes to see. Okay. The another research work is absorption based, which is talking like solvent based, amine. So we talk about different problems like degradation, corrosion. So my research group is mainly working on this assessment of corrosion, for how we can quantify this iron binding constant. Iron binding constant means corrosion affinity. For example, if you consider material of construction is iron, for mostly cast iron, then what is the affinity for MEA or different blends? So that is one area which I am working on to find out some model or some correlation between corrosion affinity and amine degradation, number of cycle. So those is the other thing, corrosion, to understand more about the mechanism. We also try to work on a new blend solvent so that it has higher absorption capacity, or mainly absorption capacity of amine has a no problem. So MEA is good, but main is the desorption temperature is very high. We need desorption temperature for MEA is around 120. So which means you need more energy. So we are looking into new solvent which is dissolved at the lower temperature. So means lower these things. So this is one area. Again, you talk about the reactor. That is a good area, like, you have the gas and liquid amine and they will absorb CO2, no problem. But how to mix those? For example, if the mixing is not good between gas and the liquid, then your absorption, the mass transfer is less, then your absorption capacity will be less. So I'm working on also on the mass transfer characteristics of the solvent and the CO2 so that it will increase the performance of the process. So it's on that. Again, the complementary CFD simulation. Again, the CFD simulation for amine based solvent is also very difficult because you need to understand all the mechanism. You have to include all the reaction for the CO2 absorption, all the reaction mechanisms, reaction kinetics, all this, because it's not simple, because you have to include kinetics, reaction, solubility, those things, again changing from phase change also from the liquid to the CO2, the gas. So all this is a part of the CFD simulation which will help for the scale up of the processes. So these are the work going on in my group. So I would like to thank my group, and finally I would like to just comment, like, how do we, for example, there are, I think there industry people here? Yes. How many industry? 50%? Oh, that's great. So this is just like, how can academia, for example, this technology, whatever, and finally it has to go to the industry, like, they have to do this. But why you might say, so what is the role of us, like, academia. So industry plays a huge role in deployment of this technology, whatever the new development. But again, they cannot develop it there, like in a large scale. They have to come. So that's how this academic role coming up, that we have to look into the future. What is the future technology? What is the future, what will be the main, for example, CO2 capture, means what will be the future direction? So energy, what is the scenario of the energy? Those things, the next step of innovation, for example, now EV, for example, now what is the battery thing, so recycling. So you have to talk about, like, academics has to think about the future. Then there is slowly research development happen, and finally it will go to the industry for deployment. And another big player in this role is government, because all the policies will come from the government. So altogether, and also academics, another very important role for academician to train the students, like for this type of course. So this is the role of academic, but again, as I said, we have to, the government, industry and academics, we have to work together to get those net zero initiative, or to maybe, I think, to live a better life. So you can say, yeah, this is the, I think, recipe for successful energy transition. So with that, I would like to thank you for listening.